Hey everyone, so just kind of picking up where we left off on page 3 in our note packet, we were talking about multiple regression, and so now we're finally kind of delving into models that are allowing us to have more than one predictor. And so we kind of talked about how to make a prediction, we talked about how to get a residual for this model, and now we're going to talk about adjusted R squared. And so the reason why we're talking about this is because adjusted R squared is like a common metric of model fit in multiple regression. And so let's go ahead and write that down and then talk a little bit more about what we mean by that. And so we're thinking about this adjusted R squared just as this measure of model fit. In multiple regression, we're also going to note that, like, remember when we did simple linear regression and we had R squared and we had that nice interpretation of like the percentage of variability in the response that could be explained with our model. So we don't have that same interpretability here. So we're kind of losing that, so we can't really interpret this adjusted R squared value aside from that it's a measure of model fit. And we're going to just make a last note that models with higher adjusted R squared are better, at least better in terms of this criterion. And so, like, why the adjusted part then? So we're adjusting it because we're including more predictors now. And so what's happening is that models with more predictors get a penalty. And so we want models with more predictors to get some sort of penalty for complexity. Regular R squared doesn't get that penalty, meaning that if I continue to add predictors to this model, regular R squared is only going to go up no matter what. So it could either stay the same or get higher, but it would never get lower. And that's not really that useful. Like if I added, I don't know, the number of pets that a person has and the whether or not they like Starburst jelly beans. And if I add all these like useless predictors, then R squared is just going to keep going up and up and up and up when those predictors are completely useless. Adjusted R squared is going to penalize for adding even more predictors, so that if I added whether or not a person likes Starburst jelly beans, I would think the adjusted R squared would then go down because it has that penalty for an added predictor. And so that's why we're including that instead of just the regular R squared. And so let's see kind of this in action a little bit. And so we've got some output from a model with just high school GPA as a predictor. The adjusted R squared is in this bottom right-hand corner, so it's 0.2945. Let's compare that to our adjusted R squared with all of these predictors: gender, the SAT math, SAT verbal, and high school GPA. That adjusted R squared is 0.364. And so take a moment just to kind of review and ask yourself, well, which model would you prefer then? All right, and so the question really isn't too hard. The model with gender, SAT math, SAT verbal, and high school GPA is preferred because its adjusted R squared is higher. So it's higher than the model with only high school GPA. Okay, so adjusted R-squared is just one of many, many, many ways that you could compare two models. It's really the only way that we're going to discuss in this class, so it's kind of simple in that if we had two models, the only criterion we're discussing to compare them is the adjusted R-squared, where higher is better. But I just want to be clear that that is just one criterion. There are many other things that you can do to compare two candidate models for their usefulness. All right, so as always, let me know if you have any questions about any of this.